Okay, so let me quickly. So I'm going to recall couple examples of Turing machines, and the reason why I'm recalling it is also to remind you about the Turing machines. But other than that, we are going to use these specific Turing machines. I'm going to recall quite heavily today and tomorrow for our lectures. So I'm not going to define a Turing machine. You all know the definition: state, alphabet, transition function, start state and accepting state. It goes both ways, left, right, neutral, and it reads k many tapes. So here are some examples of Turing machines, not these, but so this example, we're going to use this probably today. So there was this Turing machine called Shift R tape 1, and what it does, it shifts this encryption of tape 1 to the right. And how it does this is for every alphabet symbol, you had a for every alphabet. So every symbol in your alphabet, you have a here is the mouse. So you have a specific state, right? So let's say if your A consists of 0, 1, and hashtag, you will have Z1, Z0, and Z hashtag, where this 1 and 0 and hashtag are the superscripts, meaning they're upstairs here. And then you have two more states, the accepting state and the start state. And how you do it is when you read A, so you begin in your start state, and when you read A, so basically when you read A, you move to the state that corresponds to A, basically. So if you read 0, you will go, so if you read hashtag, let's say you go to Z hashtag state, and you erase your symbol and go right. So then when you're in state ZA, so let's say Z hashtag, then you read somehow B, let's say any symbol B, then you will erase B and write whatever the symbol is here. So in our case, you will write hashtag. So basically you read something, you remember it in a state, and then for the next letter, you overwrite it with whatever you have remembered. So you do this all the way up, all the way you go right, 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 unless you encounter blank. And when you encounter blank, you're in some state ZA, and you have to write A and go to accepting state. So basically what it does, it just reads the input, shifts it to the right, and ends on the rightmost part. So this is the Turing machine we are going to use. So so we assume that the input does not contain blanks. Yeah. So this is a good assumption to make. Otherwise, you can, of course, it's not essential. However, but we do make this assumption somehow. Yeah, so this is just a notation. So what it says, ZA is for any A. So for any A you have, it's just ZA, just a notation. And by B we mean something else then. So I cannot write A here also, because then that would mean that these two are the same. But in ZA you mean for any A. So in this case I took 0, 1 and hashtag, but you can, any alphabet symbol you have a corresponding state for that alphabet symbol. And you have as many states as you like. So alphabet symbols are finite, so states are also finite. But however many alphabet symbols you have that many states, and you just copy it unless you encounter B. When you encounter the blank, and again, yeah, we assume that the input, the thing that you're shifting to the right is, I mean, it has to have start and the beginning, right? I mean, how else are you going to define that it shifts right? It has to have the beginning end and the stop end, and we define beginning and the stop of the input by B's somehow. So B's is it's not a special requirement that the input does not contain B's. It's just, this is how I define my input. Input is something that is enclosed between two B's in this case. So this machine is not regular, meaning when it's finished, it's not coming back, but that's not a problem. And you can also define shift left this way. What else are we going to need here? I cannot really recall what else, but I know that we will need this shifting machine, so it's a good way to recall Turing machines by a shifting thing. So let me recall you what we were doing last time and where we stopped. I looked at our recording. So we were trying to prove that So we defined this Turing machine, so this is an abstract computer, a Turing machine, and then we had a definition before, we had a definition of mu-recursive functions. So these were functions that were created from constant functions, from projections, and from a successor, and you could compose them. You can use a primitive recursion on them, and you could use minimization on them, so this mu-minimization. And then we said that every function that is computable can be created this way. This was the Church thesis. And now we're saying that we want to restate this and say that everything that is computed is also, it's computed by a Turing machine. And in order to show that these two things are the same, what we are trying to prove is that every mu-recursive function is computed by a Turing machine. Meaning that proving this would entail proving that constants are computed by a Turing machine, projections are computed by a Turing machine, successor is computed by a Turing machine. Then if you have Turing machine computable two functions, then composition is computed this way. If you have Turing machine computable functions, then if you form a primitive recursion, that is also computed by Turing machine. And then we also have to show that now if you have a function which is computable by a Turing machine, meaning that if you put an input, then you run your Turing machine and it gives you the output, then the minimization of that function is also computable by Turing machine. And that argument would imply that every mu-recursive function, because it's constructed from these building blocks, will also be computed by a Turing machine. And we did this last time. We proved lemma 1, meaning that every constant is computed by a Turing machine. We proved that successor function is computed by a Turing machine. We proved that projections are computed by a Turing machine. Then we went on and proved that if you have functions f and r many functions g, if you put g's inside f's, that is also computed by a Turing machine. We did this last time. We also did the recursion, the primitive recursion, meaning that if we had the Turing machine computable functions g and h, we proved that if you define f this way, using your bread and butter recursion for computer science, meaning if you define f this way, then we show that you can construct a Turing machine that also computes f. Basically, this was just, we were counting down from here and so on and so forth. You can see it also in the recording from the previous weeks. And only part that was left to finish the proof was indeed this part. And this is actually a very easy part, and we have to finish it. So let's now look at this more carefully. So what does it say? So let's say now we have a function f, right? So this is an r+1 many variable function that it takes r+1 many inputs and it outputs one number. And I know that there exists a Turing machine that computes it. Meaning there exists a Turing machine for which if I give this Turing machine an input, r+1 many inputs, it will do its magic and it will output whatever this function outputs. So there exists a computer that computes this function. This is what basically this is supposed to say. So let's say it's a Turing computable, then this function, which has one less variable, which was also on your midterm, you had to compute this function from a specific function, so you know this. So this mu-f is also Turing machine computable. So what is mu-f? Just to remind you, mu-f is a function which is that returns the smallest index m, such that if you plug in m as the first variable in your function and you plug in x as x is a vector, so it contains r many variables. So it's basically x1, x2, x3 up to xr. So you plug in first m, then x1, x2 up to xr. Then you can compute f and check whether if it's 0 or not. So it checks for m equals 0, then checks for m equals 1, m equals 2, m equals 3. And the first place it finds 0, it returns that m. So it returns the smallest solution of this guy, but it might be that it keeps on checking. It's like a while loop. So while this is non-zero, it increments m, but if it never finds m, it's undefined. So it's a while loop that loops on itself forever. And this turns out to be an essential property of computation in general, that these things are very much necessary and you cannot get rid of it. We'll actually dive into this in much more detail in the next weeks, where we talk about uncomputable functions. But okay, how am I going to do it with a Turing machine? So I know that this f is computable by a Turing machine. So let f is computable by regular some k-tape Turing machine big F. So big F is a machine or a program that computes f. Now I want to compute mu f, and I am going to do it in k+2 tapes. Let's ignore it for a moment. This is a technicality. So if I needed k tapes to compute this function, I say that I need 2 more tapes to compute this function, but it doesn't really matter. So what is the setup now? So I start with the input 1 to r. So this function takes r many inputs, x1, x2 up to xr, and it must give me, so this is the input on my tape. So this is the input on tape 1, so the binary representation of x1, binary x2, it doesn't really matter, by the way. Also, we just agree to use binary because in computer science we use zeros and ones, so we just say let's just use zeros and ones, but it doesn't really matter. Think of it as x1, x2, x3 up to xr. So this is my input, and I have to run my machine on this and output the first m such that fmx is 0, otherwise I output nothing if it has no solution, so to speak. So this is actually very easy, so let's try to do this. So how do I do this? So imagine that these are my tapes, tape 1, tape 2, tape 3, tape 4. For initially, tape 1 contains my input. So what I do is I set tape 2 equals 0. This is a Turing machine that erases, so there's nothing in the beginning, so these are all blank. So we just put 0 there. Then I set tape 3 also equal to 0. So now tape 3 is 0. Now ignore this for a moment. So this is tape 1, then 0, 0. Tape 3 is 0. And then I append the input and evaluate f0x on tape 3. So let's read the actual program so it's more understandable. Tape 2 equals 0. By the way, recall that this is a Turing machine that we constructed that erases everything on tape 2 and puts 0. We gave this example. Then this semicolon means that then I run the Turing machine tape 3 equals tape 2. What this does, you can read it as some kind of pseudocode. Tape 2 becomes 0. Tape 3 becomes tape 2, which that means tape 3 also becomes 0. Then tape 3 becomes tape 3 concatenated with tape 1. So the effect of it will be that you will have 0 on tape 2, 0 on tape 3, and then you will have 0 hashtag 0. Oh no, 0 hashtag x1, x2 up to xr on tape 3. And now what I'm going to do, so on the first step, here you will have again the same. Oops, I cannot write. So let me get the pen. So here, so on step 1, this will be same. So it will be what? Binary x1 hashtag and so on hashtag binary xr. So you have this. Here I will put 0 initially. So tape 2 is 0. Now tape 3 becomes also 0. So initially I put 0 also here. And then I change tape 3, putting tape 3 hashtag tape 1. So this, what will happen here? Binary x1 hashtag so on binary xr. And then I concatenate with the Turing machine. I know that the Turing machine that computes f exists. This is big F. So I run this Turing machine on tapes 3 to k+2. So here on these tapes now, these tapes are empty, right? I run my Turing machine f. What f does, f basically computes function f. So it will compute fmx. In our case, it will compute f0x. Because 0 is just 0 and this is just x1, x2 up to xr. So I will run this machine with this input, so it will compute this, right? And okay, so then this will be computed for tape 0. So let's continue. So okay, now it computed this f0x. Now I have to check whether this is 0. If it's not 0, I have to increment by 1. So this is what the next thing is doing. While tape 3 is non-zero, meaning, so I computed f here, right? Now I compute f here, so on first step f0x. If it's not 0, I increment tape 2 by 1, so tape 2 becomes tape 2 plus 1. Then I raise tape 3. Tape 3 becomes tape 2, meaning 1 on step 1. And I do the same exactly. Tape 3 becomes tape 3 concatenated with the input. So then on step 1, this will compute f1x. Then again, it will check is this 0 now? So it will check is this thing 0. If not, again, it will erase this and compute f2x. Check it's 0, erase this, and so on. And this while loop will only terminate. So this while loop will only terminate once it finds that tape 3 is 0. If tape 3 is 0, this while loop will terminate, and then if a solution M is found in the loop terminates with, on tape 2 you will have the solution because you're writing down M at every point on tape 2, and in order to make a machine regular, you bring that M to tape 1, so tape 1 becomes tape 2, you erase tape 2 and erase tape 3. But if this while loop never terminates, meaning it never finds the solution, this is always non-zero, this Turing machine continues to work and this function is undefined. So the very important lesson here to take away is that this omega really here means that your program is running somehow. It's not like it terminates and tells you, oh, I'm undefined. So this undefined is really different than for me telling you that this is some number. Because there's no way of you knowing that this function is undefined. Let's say if you wrote this program and this while loop is running and then you started it and then you're waiting. So you have no way of knowing whether this program will stop and produce a number or it's undefined. So it's very different from, even though mathematically I write that it's undefined, somehow you will never be able to know that it's undefined. That's what I'm trying to say here. And before we go on, I might as well stop this and you. So okay, so now we move on to more models of computation, and we are gonna define now, we are diving in a little bit into complexity theory, like P equals NP and time and space complexity. This is a huge topic, but the reason why I'm diving to this, I will explain you right now. Why am I doing all of this at the moment? So what we proved, let's recall. So we proved now that, so what did we prove? That if you have a mu-recursive function, then we just proved that it is computed by a Turing machine. How did we prove this? We proved that constants are computed by Turing machine, projections this way, composition, blah, blah, blah. So we proved this. So now every mu-recursive function is computed by a Turing machine. What I want to, so for this, I used that if I had a mu-recursive function, f, I constructed a Turing machine which had k tapes. So now this is again the same story as we had with DFA and NFA. The story is the following, is that if you give me a mu-recursive function, right, let's say constants, or let's say primitive recursion or whatever, and I have to construct a Turing machine, it's very handy to have k many tapes. Because if I have k many tapes, I can construct more complicated Turing machines, you might think. So if you give me a function and I have to construct a Turing machine, of course it's good to have as many tapes as I like. But now what I'm trying to prove is that, let's say f is computed by a Turing machine. This means, let's say f is a function such that when I start my Turing machine on the input, let's say x2, x3, x4, let's say it has 5 variables. So let's say it's n05 to n. So I run my Turing machine and it outputs whatever. X, output X, that would mean that fx1 to x5 is X. So for my function, let's say there exists a Turing machine that computes it. I want to prove now the other way around, that this is mu-recursive, that f is mu-recursive. Now, my Turing machine will be completely general, right? So if I tell you, let's say f is computed by a Turing machine, prove that f is mu-recursive, then this Turing machine has to be completely general for this thing to work, right? I cannot, so f is computed by a Turing machine, that means this Turing machine has k-tapes. What I want to prove now, that if a function is computed by, whatever can be computed on k-tapes can also be computed by one tape. The same exact way I proved that NFA and DFA are the same, because it was easier to prove something for a DFA. The same exact way, I'm going to prove now that k-tape Turing machine is exactly the same as one-tape Turing machine. And then if I know this, I can assume that my f is computed by one-tape machine and prove that f is mu-recursive. That would be easier. See the point of proving? So it was when I was going from left to right, it was easier to use k-tapes. But now when I'm going from right to left, I put on the restriction that my function is computed by one tape machine, and that would make it easier to prove that something computed by one tape machine is of course easier to prove. Well, you might think it's easier to prove that something computed by one tape machine is mu-recursive than something computed by k-tape machine. And for this, I need an intermediary step. The Turing machine on k-tapes is the same as Turing machine on one tape. The only reason in the beginning I introduced k-tapes is because it's easier to program. The same exact way we proved that NFAs and DFAs are the same. I mean, why the hell did I introduce NFAs at all? Because they're more complicated. The reason is because it's easier to program, like epsilon moves and stuff, because you have more freedom. Here also, it's much easier to work with k-tape machines sometimes. For example, when we were copying the things and shifting, doing stuff, it's easier to like copy it down than put it up or something. So it's easier for programming, but we are going to prove now that they're no different. And in many textbooks, definition of a Turing machine is you just have one tape, one head, which moves left, right, and stays the same. Even in the exercises, there are even more restrictions. You can think that tape is only infinite to one side and stuff like this. But the first thing is one tape Turing machine. However, even though computationally one tape Turing machines and let's say 2 tape and 3 tape and million tape Turing machines are the same, there is a trade-off. The trade-off is that whatever you can do on 2 tapes, let's say in n steps in 2 tapes, can you do it the same thing in n steps on 1 tape? That is, I mean, you will lose time. That's the idea. Even though it's still the same computationally, it takes more time. Like for example, so we'll see in a minute why this is true.
And how does the time scale with the amount of tapes we have?
Exactly, we're going to address this now and show you exactly how the time and space scales and what it actually means for time and space to scale. So the question is, how powerful are one-tape Turing machines? And the answer is as powerful as anything you have seen, meaning from computer science standpoint, one-tape Turing machine is everything that can be computed on a one-tape Turing machine. That's Church's thesis. But we're still in the support of it. But now we're going to simulate. So what we're trying to do is, of course, if you can compute something on 1 tape, you can compute it on 2 tapes, right? That's obvious because you do nothing on second tape and it's the same. But now what we are going to do is that we're going to have a machine that does something on k many tapes, let's say 10 tapes, and I want to simulate the same exact do the same exact thing on 1 tape. This is what I'm going to do. And meanwhile, while we're doing this is called the simulation theorem, because you're simulating k tapes on one tape, we are going to count what is the trade-off. And the trade-off is the time it takes and space it takes. So you can think of it as time your computer takes, and space is like the hard disk it occupies to do this. And since we're doing the simulations, might as well actually see what this time and space trade-off is, and then we will use this later for our, when we move to complexity theory, we will heavily use these things, T and Sn. So let's give definitions. So definition is T is a time or space-bounded Turing machine. So what is a time-bounded Turing machine? A Turing machine M is Tn time-bounded. Tn is a function now. So think of it as a function. So I have two functions, imagine. So let's write it here. So Tn is a function from natural numbers into natural numbers. 0, let's say. And so is Sn. So I have two functions. So for example, just Tn can be n squared. I don't know. Or Tn can be n log n or something like this, right? So it's like a polynomial function. Sn can be also some function like n cubed plus 3, whatever. So these are just functions from natural numbers to natural number. And I will say that Turing machine M is Tn time bounded. So let's say n squared time bounded. So the machine will be n squared time bounded if for all n and every input w of length n, machine M started with w makes at most Tn steps. So for example, let's take Tn equals, I don't know, n squared. Let's say n squared plus 3 again. This means that I will say that the machine is Tn time bounded, is that if I start this machine on input of length 3, let's say, so the input is of length 3, let's say w is what? 0, 0, 1. This is my input, so let's say it has length 3. If I start my machine on this input, 0, 0, 1, it doesn't make more than 3 squared plus 3 steps, which is 12. So it doesn't make more than 12 steps, right? So that would be, but this must work for any n. If I take a different input of a longer length, then when I start my, so what is a step, by the way? Step is the head movement, or every transition function application is a step. So it might be that my machine stays in the same place, but it's still making a step because it's using a transition function. So you count how many steps does it make until it ends. And once it ends, it should not make more than n squared plus 3 many steps if your input had length n. That would be a Tn time-bounded machine. So question number 1. Does a Tn time-bounded machine halt? Does it have to halt?
Yes.
Yeah, so this is the first assumption, that every time-bounded machine has to halt. If your machine goes on forever in a while loop, like we saw before, it's not time-bounded at all. It has no bound. You cannot come up with a function that bounds it. So this is a time-bounded machine. So what is a space-bounded machine? Now, look at your machine. Your machine can make infinite steps. However, it might maybe move between two cells only. So it makes infinite steps, but it just moves between two cells back and forth, back and forth. It's not time-bounded, but it's space-bounded. So I also can measure how many cells my machine is visiting. So it looks at the tape and you just count how many cells this machine is visiting. So a TMM is Sn space-bounded. Sn is just another function. It can be the same thing. So let's take the same guy. So let's say Sn is again n squared plus 3. So my machine will be Sn space-bounded. Again, if for all n and every input w of length n, machine M started with w, the number of tape cells visited or occupied by the input. This is the assumption we make, because when you start an input of length n many cells are already occupied, right? So I always assume that my Sn is bigger than n, because somehow you already used n's to, even at the beginning you already used up n cells, even though you never went there. I count that Sn is n cells are already used up. So this is If M started with W, the number of tape cells you visit or occupied by the input is at most Sn. So again, if your input is this, again, you get 12. So 12 bounded Turing machine means that when you started with this 3 cells, you at most visited 12 cells in total, including the input. So when your machine has finished, you only visited 12 cells. So now the same question. Does space-bounded Turing machine have to halt? No, so this is the difference. Your machine can be space-bounded, but it doesn't have to halt. If it just goes between the cells, or even just stops at one cell, that will be space-bounded. It just visits one cell, but it never stops. It just loops on this cell. That can happen. So the fact that machine is time-bounded means that it halts. And the fact that the machine is space-bounded means it doesn't mean that it halts. However, machine can also be space unbounded. If it goes right all the time, it has an unbounded space also. It uses infinite space and you cannot bound it. So this will be the things that is considered in complexity theory completely. And by the way, some books consider tape bounds that are less than n, so meaning they do this. And what they do usually is that they have an input tape. So you can imagine your machine has just one tape only for input and you're not allowed to work there. You only read this input and you only work on the second tape somehow. So you have a read-only input and then you only count the cells visited downstairs somehow. Do not care about the input. You can do that, and so we do not do this, but this is just the mere. This is just nothing. I mean, it's a technicality. But we always assume that you have a one-tape Turing machine. By the way, this thing was a one-tape Turing machine, and it doesn't have to be one-tape Turing machine. Why did I say this? It can be as many tapes as you like. You just count how many steps you made, and you count how many space you occupied as a sum on all tapes. And now here comes the main theorem, and it shows you the trade-off also. This is like called the mother of all simulation theorems, means that every function computable by a k-tape Turing machine M is also computed by just one tape Turing machine M prime. And here are the trade-offs. So this is what we said before. So what will be the trade-off? The trade-off will be that if your M, this k-tape Turing machine, was Tn time-bounded, meaning it was making at most Tn many steps. Tn is just a function, let's say n log n. So if your machine was not making more than n log n steps, then your one tape machine will just square it. Meaning that if your M was Tn time-bounded, then your M prime will be big O because those constants appear. This plus 1 minus 1, we don't care, but big O t squared n plus n times Tn, which is Ot squared n, by the way. So this much time bounded. So the trade-off is you square the time. So if you were using, let's say, n cubed amount of movements to decide on your length input n whether you accept it or not, or you output whatever, then you would need n to the fourth amount of many steps. So it squares the time, but in case of space, it doesn't really change anything. So if M is a Sn space bounded, then M prime, which is just one tape machine, will be Sn plus 2 space bounded. So you just need 2 more cells and that's it. So it basically stays the same. If you put big O here, it's the same. So if f does not read the whole input, we might have Tn is less than n, but we don't care about this. So, okay, now can anybody actually think about how will this thing happen? I see you did this somewhere in a disguise in one of your other classes. No. Wait. It's still recording? Yes. So let's go back here and see how would you want to do this. Let's say I have a machine, so this is like a question that works, let's say for simplicity, on 2 tapes. So you have something here that you do something here from your control, and I want to do the same thing on the 1 tape. How would you do this?
Can't we just put those 2 tapes together, and for each pointer we could, like, for example, I want to work on the 2nd tape first, right? So
let's address it one more. So put together, what do you mean? Put side by side like this. But so let's say, okay, let's say, so what let's say it's like 3, 4, 5 x hashtag here and 0, 0, 1 blank 1 here, and then there's blank 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 blank, and you want to put them, but how would you know where this guy? So let's say, so you want to put something like this, 3, 4, 5 x hashtag, and then continue with 0, 0, 1 b1 like this.
Maybe we could add a separator like hashtag and other symbol that indicates the start of a new tape.
So maybe, yeah. So you put something here, and how does so now your head is here. What this can do is this can read 5 and 0 at the same time, right? And make a movement. Let's simulate one step. Let's say this guy is in state Z, and it reads 5 and it reads 0, and it, let's say, just overwrite this one, overwrite this with blank. It goes here and it goes here. How will I do this? The same thing here.
Good question.
Because I mean, you can read 3, which is here, but somehow you have to find where you have to find 5, and then you can have to find the correct 0 here, erase this 0, overwrite this 1, erase this 5, overwrite this with blank, and then going right and going left has to also somehow.
თავში დავწეროთ, აი 5 და 1 თუ იწდება, მაშინ 5 და 1 დავარქვათ იმ starting points რა, როგორც DFA-დან NFA-დან
როგორ?
აი პირველი tape ზე ხო არის მიმართული ის არის. აი მარცხნივ. და მეორე tape-ზეც არის რაღაც ის არის, ხო? და ეგ ისრები ერთ ხაზზე გავაკეთოთ თქო რა. ეგრე წარმოვიდგინოთ. და ეხა ახალი tape რო გვექნება ერთიანი.
ერთი tape უნდა იყოს.
კი, ერთი tape უნდა იყოს. და ეხა მან სამე თავი ის არის გავაკეთოთ, საიდანაც ვიწყებთ. ხო, აი მან მაგას დავარქვათ, აი აქ რადგან დავიწყეთ 5-0-დან.
Let me pause the recording and we do this. So unfortunately we lost like an hour of recording, and hence I'm gonna just do a really quick rundown so people who do not have access to slides at least can pause and ponder and actually look at slides at least. But I'm going to do it very quickly because there was like an hour of recording, as I said, and I'm just going to give you rough ideas and leave others as an exercise. So what we're trying to do is we're trying to prove this theorem that we can simulate a k-tape Turing machine on a 1-tape Turing machine, M prime. M is the name of a k-tape machine. And if M was doing everything in time Tn, we will need the squared amount of time. So we have OT squared n plus n times Tn. And the space is essentially stays the same. So we're using the same amount of space. So here is the main idea. Let me just explain it very quickly. What is the main idea here? The main idea was actually guessed by students correctly. It is that so you have let's say 2 tapes like this. Then you have a machine that operates on these 2 tapes, and now I want to simulate, let's say, this on 1 tape. Is that, let's say my alphabet here was just 0, 1, blank and hashtag, the minimal alphabet that we always assume we have. Then what I will do is I'm going to compress the tapes into an alphabet basically. So I'm simulating this on one tape. However, my one tape is now contains tracks. And what are these tracks? Basically what I'm doing is I'm basically changing my alphabet into vectors. So here I should be, so let's give it an example. So let's say something like this. And let's say 0, 1, 0, 1, 1, 0, 1 blank, hashtag 1, 0, I don't know. So something like this. So what I'm going to do, and let's say it's instead state Z4, I'm going to write a triple here like Z4, 0, 1. So basically now this is again one cell, but my alphabet has the symbol, a vector of a triple Z4, 0, and 1. And here I will write blank whatever, blank 1, 1, maybe just blank here like this. So I'm able to write down the vectors so that the 0 component of the vector on the first component is either a state or a blank symbol. The second and third components of this vector, in case of two tapes, will be just whatever can be written on first and second tape. And then I also can write the symbols themselves on my tape. So here I will not do this, but if I want to, I can also write things like this. Right? So basically what this mathematically entails is the following, that say that if my initial machine M, which is a K-tape machine, has the alphabet 0, 1, B, hashtag, and some other symbols. So we always assume I have 0, 1, B, and hashtag. So that means I can write my alphabet as the union of 0, 1, B, hashtag with something else, whatever this something else is. And I want to simulate this. I will blow up my alphabet basically. So what is my new alphabet that I'm writing on one tape? So this is the alphabet of this one. What is this supposed to have? This alphabet has all the symbols that I had previously. So A's here. These are to show that I can write this one symbol on a tape again, like things like this, as I said. And then now it has vectors, as I said. So it's like a k plus one dimensional vector. Here you can see that this is a k plus one tuple, basically, such that, so instead of using 1 to up to k plus 1, I will use from 0 to 1. So the 0th component of this vector is either a state or a blank symbol, like here. Here is the state, here it's blank, and all the other components can be anything from A. So basically here I wrote zeros and ones. So this is what I'm going to use, and to simulate the situation that I'm state Z4 in 0 and 1, I will write Z4, 0, 1. The whole idea is that also remarked by you students, that if this thing moves right, let's say, and let's say it moves left here, how am I going to simulate this? Let me erase this. So how am I going to simulate this here is whatever happened at this cell when I overwrote this one, and let's say also with this one, I will overwrite this here, and I will shift this track. If the head movement on tape 2 was to the right, then I will have to shift this, they call it a track, this track that I circled, to the left, basically. So head movement to the right of the machine that I'm simulating, it's the equivalent of shifting this track to the left, and the head movement to the left of the machine is the shift of track to the right. So maybe I'm mistaken. So track 1 is this guy here, and track 2 is this guy here. Doesn't really matter, but so if the head moves left on track 1, then I'll have to move right. So if head moves left on tape 1, I have to shift track 1 to the right. But I mean, somehow I call it a track, but it's basically nothing, but I'm operating still, this is like a single cell and single tape. So shifting a track means erasing everything here and then writing the same thing like Z4. Well, if I shift it to left, it's still 0 here, 1, but you get the point, right? You can shift the tracks left and right. And you basically guessed it during the lecture, so I'm not gonna dive too much into this since it's like a makeup that I'm a really quick rundown, but this is the basic explanation of the idea. And so here is the picture that, again, it's the same picture I drew. So on the first track here you have state and all blanks. On the second track you have whatever happens on the first tape. On the third track you have whatever happens on the second tape, and so on. It's on this picture, it's called spur, or it's track, spur, these are the same things. So you're simulating this situation this way. And in order to do this, you have to first do the pre-processing somehow. That means that when your machine starts in the initial configuration like this, so this is your input. Let's say if it's a K-tape machine, this is on tape 1 and all other tapes are empty, then you have to really simulate this situation this way on your one tape machine. This is one tape machine, by the way. Let me just remind you, this is like tapes are like this. And this whole vector is written as one symbol on one tape. And what you have to do is you have to kind of change this into this. Of course, it can be done. How do you do this? First, you write this symbol on track 2 or track 1, and then you write the start state on track 0. So you write something like this, W1 and all blanks. And then on here you write blank, W2, all blanks, whatever. But I mean, the interesting part is how many steps do you need for this? And there's an explanation that you need 2n plus 4, maybe it's 2n plus 3, and there's a typo. And you can figure it out. So how many steps would I need to do this? Well, let me explain to you very quickly why would you need 2n plus something. So first, on the first track, so first you have to write start state and W1. Then you have to move right blank, W2, blank, 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 this vector here. Then move again. You have to make n many steps to get to here, write Wn. Then you have to make one more step to go to the blank symbol. Once you read the big blank symbol, by big blank I mean it's not a vector, just a blank. Then you start moving back. You again have to make n steps, again cross over to the blank symbol, and then one more step here. So in order to get this configuration from this one, basically, it was written on your tape, you really have to make what? N plus 1 plus n plus 1, so it's maybe 2n plus 3 or whatever. And then you have to go back here, so you have 2n plus 3 or something, so 2n plus 4, I don't know what this is. So okay, so you make it 2n plus something steps to do this, and in terms of space, it's n plus 2 space, because you're operating again on n cells, and one to the left and one to the right. So very quickly speaking, so you do pre-processing like this, and now only place I have to explain how this works is exactly, I have to simulate the K-tape machine. So basically what this says is, so you basically, how do you simulate this step? And you do this by, so your delta is, so your m prime is the one tape machine, right? Just let me recall. And your m is a K-tape machine, and your delta is a transition of a K-tape machine. So if your K-tape machine is state z, reads a1 to ak, goes to state z prime, overwrites with C1 up to CK, and makes movements S1 to SK, then as I said, what you have to do is on track 0, so on your zeros index of your vector, you replace z by z prime, that's of course. Now on your, also on other components of your vectors, you overwrite CIs with I's basically, right? So your CIs, you overwrite AIs by CIs. So by the way, I don't know if I mentioned that AI is so A1 is on track 1, basically. So track 0 is for state, and AI is on track I. So basically, so you overwrite CIs, and the most important bit is the movements that you make. So if the ith head goes left, right? So M moves head I to the right, right? Well, So if the head moves right, what you have to do, you have to shift your track to the left, of course, right? So if you think about it, if your head moves right, your tape on which this head is standing moves left. So you have to, your track does the opposite of the head movement. So if your head moves left, so if head of M on tape K moves left, then track K has to move right, be shifted right. And the big observation here is that once you do the shift on your tracks, you have to visit all the cells basically, because remember we recalled how the shift works. So how the shifting works is you have to visit all the cells that have encryption on them. So for every one step that the K-tape Turing machine makes, you make as many steps as there are things written on your tape. So basically this is what it says here. This is what it says here, basically that it takes time and space OS. This is exactly what I said, but this can also be left as an exercise. But then there's a sentence that says this might require to divide symbol B into tracks. So what this means that once you're shifting a track, and if you were shifting, and then you came to this big B somehow, now it has to be, something has to be shifted right here. So what this might require is that you divide big B into the vector of small b's. But you can, of course, again, figure it out. And you do it left, right, and so on. And the exercise, I will leave it as an exercise, that this takes time and space OS. If the non-black portion of the tape M1 has length S, M prime has length S, but I just explained this. And once you do this, so you do the pre-processing of the start state and the word, then you do this movement, and in the end you arrive at this situation. So when you're in, so once you see the accepting state on your zeros track, so the zeros component of your vector, once you see this, then whatever is written on your track 1, basically the second component of your vector, is what should the output be, and everything else should be erased. And from here you go to here, and this again takes space at most S if the non-black portion of the M prime is S. So why? Because you just have to go through everything, erase, and then once you see what anything on track 1, you just print it to a bigger version of it, right? Because it's also available in your alphabet. So that was also very quickly. This is post-processing. And then we extensively talked about it in the class, that why can I always assume, always meaning for other Turing machines as well, this, but why this is specifically true here is that every step that you make, basically, so maybe this is the better way to see it, that every new cell you visit, you have to make a step, right? So every time you increase Sn, you also increase Tn, but however, you might make steps and not visit new cells. So once you're increasing Tn, you might not be increasing Sn. And there's an n here because the input the input only takes up n. So every additional, so this n is already goes into Sn somehow. So every step that you make might so every increase of Sn will increase Tn plus n, because this n is already occupied by the input. So we talked about this extensively, why this is less than this, but it's a good exercise for you to think about it, that in general you can always assume this, but assume this in the sense that you can always increase this and stuff. We'll talk about this extensively later. And again, looking at our observation, we find that we talked about that every single step that your K-tape machine makes is, so you need to shift the tracks, right? So if there's every one step that the K-tape machine makes, your simulating one tape machine has to make at least as many steps as there are cells occupied. So every step needs Sn many steps, OSN many steps from a one tape machine. So that means T, if you want to simulate T many and Tn many steps, you would need Sn times Tn. So the number of steps that your one-tape machine is making is bounded by the number of steps that the k-tape machine is making times Sn, because every single step needs Sn many steps in the simulation. So this is again true, and then we substitute this inequality for Sn here, and then we multiply and we get the quadratic blow-up. But I also advised again that in your textbook there is another proof of this. As I remember correctly from last year, it's not very rigorously proven. It's done for only 2 tapes, simulating 2 tapes on 1 tape. But then if you have this, you can of course inductively simulate k tapes. But, and it's, I don't remember if the proof is rigorous, but it's, I remember that the proof is given in that textbook, so that quadratic blow-up is more maybe intuitive. But here as well, if you think about this, unfortunately, this, as I said, this is a makeup recording, so I had to go really fast. So if you think about it, also the quadratic blow-up is clear. And then we said that this random access machines, we skip all this, we do not do this. Unfortunately, we do not, otherwise we're gonna have to skip more important things later on. And then there's also very nice simulation lemma that it turns out that k-tape Turing machine can be simulated by 2 push-down machines. This is actually a very good exercise. You can read up on this, that 2 push-down machines simulate a k-tape machine. That means, by, if we believe in Church thesis, the Turing machine version of it, that 2 push-down machines are enough to simulate everything that is computable. That is also interesting. And yes, we skip this. And then, okay, tomorrow we are going, what we're going to prove tomorrow or next week, whenever our next lecture is, that going back to what we discussed before, is that we proved before that now if you have a mu-recursive function, then it can be simulated by Turing machine. Now I want to prove that if I have a Turing machine that computes some function, that some function is mu-recursive. But now what I proved, or gave a sketch, is that any k-tape Turing machine can be simulated by 1-tape Turing machine. So I might as well, without loss of generality, assume that the function that is computed by a 1-tape machine. That will make my life easier. So I will assume that M is a 1-tape Turing machine and it computes some function that I want to prove. There should be F here, that function is mu-recursive. And this requires some nice ideas that are mainly due to Gödel, I believe, but this dual was proved by Church, who was teacher of Turing. So we're going to do this next week.